Hey everyone, in this video, let's take a look at question 39, combination sum on LeetCode. This is part of our blind 75 list of questions, so let's begin. In this question, we are given an array of distinct integers, candidates, and a target integer called target. We want to return a list of all unique combinations of candidates where the chosen number sums up to target. You may return this in any order, and the same number might be used in candidates an unlimited amount of times. Two combinations are unique if the frequency of at least one of the chosen items is different. And we don't need to worry about this one. So before I get started in the question, just the moment you see something like generate all types of or list all types of or anything in which you have to do exhaustive search, you want to think about recursion, more specifically backtracking. So we've done this in our permutations question, we've done this in our subset question. And the good thing about these types of questions is that a lot of the format is exactly the same. And if you watch my subset question, if you haven't, go ahead and watch that one because I've kind of explained there like the generic format and like how we want to approach these types of questions. I'll try my best to do it here as well, but that video is really helpful. But basically, we're just going to be following a simple idea just from that. So before we get into any of that, let's just actually go through the examples here to make sure that it makes sense to us. Okay, so here we want to form a target of 7, and we have the following. So it looks like we can reuse 2 to make 4, and then 4 plus 3 gives us 7. We can also just use an element on its own to get 7, so that's perfect. Now in the next set, where we have 2, 3, and 5, we want to form 8. So notice how we can just keep using the 2 to get 8. We can do 2, 3, 3, reuse 3, and then we can do 3 and 5. And in this one, it's pretty much impossible. Now, important thing here is that all of the elements, it looks like they are positive, right? So we don't have to worry about that. Okay, so how might we go about approaching this? Well, as I mentioned, whenever you see these list all, generate all, exhaustive type questions, you want to think backtracking, right? And it kind of makes sense if you think about it. I just don't want to say think backtracking, but like it kind of makes sense if you think about it, right? Because we might generate something. Like let's say we generate something like 2, 2, 2, 2, 2, and we realize this doesn't work, and then maybe we go back, and then the next element is like a 1, and we realize this works. So that's why like backtracking should just become like intuitive in this type of question. So if you watch my subset or permutation, the way I like to approach these types of questions is I like to have a result variable, and then I like to do my recursive call here, and then I return my result variable. And the result variable basically is my result, and my helper will populate result with the potential answers, which in this case are like the potential candidates. Okay, so now let's go ahead and code our helper function. And again, I'm going to be using the same exact format that I have in subset. So a subset permutation, they often all use the same thing. So what are a couple of the things we need, right? So we need access to the candidate, and I'm just going to call this nums. Don't want to spell out candidate, so I'm just going to call it nums. What else do we need? Well, we need res. We need cur. Cur will be like our existing set of candidates that we're forming. We need the index, so we need to know like where we are in the list, and that should pretty much be it. Okay, perfect. So what else do we want to do here? So when I'm starting off this function, right, I'm going to be starting off at the current index, so index number 0. And now I really want to think about something. I'm starting off at index number 0, right? In the subset case, we always move towards the right index. In the case for permutations, we stayed on the we actually went back to the 0th index. In this case, what do we want to do? Well, if you think about it really, if we start on this index, because we can reuse this item again and again, it really makes sense if we actually just stay on the same index. So when we are doing a recursive call, we should just pass in the same index because it's possible that we might be able to reuse this element again and again. Now you may wonder, well, if we just keep passing in the same index, how are we ever going to move forward in the loop? Now, that's a good question, but realize that we have access to the target. So if we are reusing the same index and we keep adding and we somehow go past the sum, go past the target, well, then we know that we should recurse back, and then at this point we will go to the next index. So that's something to note here, that we can actually just stay at the current index, and if we ever go out of bounds or we go overboard, at that moment we'll go to the next index. So let's kind of start with that, and we'll see how we can work from there. So what we can do is we can do for I in range, we'll do index to length of nums, right? And so now one thing we need to do is we want to add this existing element. Again, this is all part of the subset, all part of like the way we do these types of questions. We want to add this existing element to cur. we will do a recursion here. We're passing nums, res, cur, and I will stay on the existing index. Then you'll finally pop it, right? Now, the question is here, how do we know whether we are, are out of bounds, basically? Like, how do we know if we have already passed the target? So one thing we can maybe check is we want to check if before adding this nums at I, if we were to add this nums at I, are we able to basically get out of bounds? So one way we could do that is we could keep track of like a current target variable, right? So not a current target, but like total sum, I guess. So we can do like total sum here, right? And the one thing we would do is we would do if total sum plus nums at I, if this is less than, or sorry, if this is less than or equal to what? Target, right? Then only we will consider this. If it's greater, then we have no reason to consider this because it's not going to lead us anywhere. It's like if we're like 2, 2, 2, 2, and then the last two actually took us like out of bounds, then we don't need to consider this. So we will keep track of this total sum here. And so what that means is we actually need to update this total sum. So we will do total sum plus what? We will do total sum plus nums at I. So this will increment the total sums. Okay, so that's perfect. Now we actually need to know where we add to the res variable, where we add to this, because as we're doing this recursion, we will keep appending to cur, but we haven't added to res yet. So we can actually just check that here. We can do if total sum is equal to target, which means actually we need to pass in target here as well. If total sum is equal to target, then we add it to res. So we can do res.append. Sure. Remember, we always append a copy, and then we return because there's nothing more to do. Even if we like go into the loop, we're just going to be out of bounds because we're going to keep adding on elements. And that's pretty much all there is to this. So we'll do res, or nums, res, curs is empty. Index will always start off as 0. Total sum will be 0, and target will just pass in. So let's take a look at this again. Let's first of all run it to see if it works or we run into any sort of bugs. Okay, so it works. Let's go ahead and submit it. Awesome, it works. So again, let's just take a look at what we did here. So we can ignore this part, but basically we are looping, and we're first making sure that my total sum and the current item does not exceed target. If it doesn't, then we'll add the target, or we'll add the current num to our list of potential candidates, and then we'll update our total sum, and then we will check to see whether we are equivalent to our answer. If we are, then we will append it, and then we'll simply return. Otherwise, come back. In any sort of way we come back, either we go out of bounds, or maybe we return because like we found the target, and then we just come back and we pop. And so that's this question. As for time complexity, I don't know. I honestly don't know. I think it's pretty hard to determine these ones, especially like backtracking questions. So you can definitely look in the description. Yeah, but these ones are usually like they have really strange like time complexities. Like you can see like 2 to the target times k. Like what the hell, right? Like, anyways, I hope this video was helpful.